Module 7, Lecture A, using torch.compile. By the end of this lecture, you will be able to describe the purpose and high-level behavior of torch.compile in PyTorch 2.10.0, wrap existing nn.Module models with torch.compile and configure basic compilation options, and measure and interpret performance changes after compilation, including warmup effects. Core compile concepts: eager and compiled modes. In PyTorch's eager mode, each operation runs immediately as Python executes the line, which makes it easy to inspect results and debug interactively, much like working in a scientific notebook. This style is flexible and convenient for development and experimentation. However, it adds overhead from the Python interpreter and the dynamic framework. For small tasks, this extra cost is usually minor, but for large models or latency-sensitive applications where operations are repeated many times, the overhead can become a significant performance issue. In PyTorch 2, compiled mode changes how models run by first analyzing the sequence of operations instead of executing each step immediately. The system observes the model, captures its operations, and builds an optimized version that can be reused. This reduces Python overhead on later runs and allows the computation to execute more efficiently. The compiled model behaves the same as the eager version, but it is faster because operations are combined and results are reused more effectively. In PyTorch, eager mode and compiled mode aim to produce the same results, but differ in how they run your code. Eager mode executes operations immediately, making it flexible and easy to experiment with and debug. Compiled mode instead focuses on performance and consistency, which is especially important for production models. It may take extra effort at first to optimize compiled mode, but once tuned, it usually runs much faster. Understanding this trade-off helps you choose between the convenience of eager execution and the efficiency of compilation for demanding workloads. Python code: eager and compiled modes. This script compares two ways of running a simple model: eager execution and compiled execution. It uses TensorFlow to imitate the compile style found in PyTorch. The main goal is to measure and compare how long the model takes to run in each execution mode. By timing these runs, you can see the performance differences between eager and compiled execution styles. The commented line is a reminder to install TensorFlow version 2.20.0, which the script depends on. It indicates that the code may use features specific to this version, so having the correct version installed is important. Because the command is commented out, it should be run separately in the environment where you plan to execute the script. We begin by importing a few key modules that the script will rely on. The operating system module lets the program interact with files and the system environment, while the random module is used to generate random numbers. The time module helps measure how long parts of the code take to run. We also import the numerical computing library NumPy and the machine learning library TensorFlow, which provide tools for efficient calculations and for building and running machine learning models. Together, these imports prepare the environment so the rest of the code can use their features. We begin by setting a seed value, such as 42, so that all random operations become reproducible. We first set the seed for the standard random library, which controls the random numbers it generates. Then we set the seed for the NumPy random number generator, so that any random arrays or values from NumPy are consistent each time. Finally, we set the seed for TensorFlow's random number generator, so that operations like initializing model weights behave the same on every run. By setting these seeds, we create a controlled environment where experiments can be repeated reliably. This code simply prints the version of TensorFlow that is currently in use. Knowing the exact version is important when you are debugging. It also helps you check that your TensorFlow setup is compatible with the rest of your code. The code first checks whether any GPUs are available by asking TensorFlow for the list of physical GPU devices and turning that result into a simple yes or no. If at least one GPU is found, it chooses the first GPU as the device to run on. If not, it falls back to the first CPU. This approach automatically selects the best available hardware so the model can benefit from GPU acceleration when possible and otherwise run on the CPU. We build a simple dense neural network model using the Keras sequential interface in TensorFlow. The model takes input data with 32 features, then passes it through a dense layer with 64 units and a ReLU activation to add nonlinearity. It ends with a dense layer of 10 units using a softmax activation, which produces a probability distribution over 10 possible classes for multi-class classification tasks. To build the model, we first create a dummy input tensor filled with zeros, shaped as 1 by 32 and using floating point values. We then pass this dummy input through the model in a forward pass. This process initializes the model's internal structures and parameters. As a result, the model is fully set up and ready for real computations in later steps. The code first runs a dummy input through the model to find the shape of its output, then converts this shape into a list for easy comparison. It checks whether this output has the expected size of 1 by 10. If the shape does not match, it raises an assertion error with a message about the unexpected output shape. This validation step ensures the model is producing outputs of the correct dimensions before any further processing is done. We begin by choosing a batch size of 256, which sets how many samples are processed at once. Using TensorFlow's random normal data generator, we then create input data with this batch size and 32 features. The values are drawn from a standard normal distribution, meaning they are random but follow a specific statistical pattern. This synthetic input is used to test how our model performs under different execution modes. The eager forward function takes a batch of input data, passes it through the model, and returns the resulting output. It runs in eager execution mode, which means each operation is carried out immediately as the Python code is executed. This immediate execution makes the flow of computation more intuitive and helps with straightforward debugging. This function runs a forward pass through the model using TensorFlow's compiled execution mode. By decorating the function, TensorFlow converts it into an optimized computation graph, which reduces overhead and can speed up execution. Inside the function, the model takes an input batch and produces output predictions. This approach is especially efficient when the model is called many times. This function measures how long it takes to run another function multiple times. It accepts 3 inputs: the function to test, the data to pass into it, and the number of warmup and timed runs. First, it performs several warmup runs where it calls the function with the given data but does not record the time. This warmup phase lets any initial setup costs occur before measurement. After that, the system is prepared for more accurate timing in the main measurement phase. We begin by recording the current time using a high-precision performance counter, which marks the start of our timing. Then we run a loop for the specified number of timed runs. In each iteration, we call the given function with the provided input batch. By executing the function many times, we can measure its performance more reliably and compute an average runtime that is less affected by random variation. The code records the current time with a high-precision performance counter to mark the end of the timing sequence. It then subtracts the start time from this end time and divides by the number of runs to find the average time per execution. This gives an accurate measure of how long each run takes on average, which is important for comparing the performance of different execution modes. We begin by running the code 3 times as a warm-up to reduce any initial overhead before measuring performance. After that, we time 10 runs of the actual execution. Using multiple timed runs lets us average the results and get a more reliable comparison between eager and compiled execution modes. We first choose the device context in TensorFlow so that the next operations run on either the GPU or CPU, depending on what is available. Inside this context, we call a timing function that receives the eager forward pass function, the input batch, and the number of warm-up and measured runs. This procedure lets us compute the average time needed for forward passes in eager execution mode. The result serves as a baseline to compare against the performance of the compiled execution mode. To measure execution time in compiled mode, we first choose the device, such as a CPU or GPU, using TensorFlow's device management, so all operations run on that hardware. Inside this device context, we call a timing helper that runs the compiled forward function, which is a TensorFlow wrapped version of our model, optimized for performance. We pass it the input batch and specify how many warm-up and timed runs to perform. This process gives us an accurate average time for the compiled model to process the batch, which we can then compare with the time from eager execution. To compute the relative speedup, we first check that the compiled execution time is greater than 0, so we do not divide by 0. If it is, we calculate speedup as the eager execution time divided by the compiled execution time, which tells us how many times faster the compiled mode is than the eager mode. If the compiled time is 0 or negative, which is unlikely but still check for safety, we simply set the speedup to 1, meaning no speedup. We first report which device the model used, either a graphics processor or the main processor, depending on what is available. Then we show the average time the model took to run in eager mode, rounded to 6 decimal places, followed by the average time in compiled mode with the same precision. Finally, we compute the speedup factor as the eager time divided by the compiled time, rounded to 2 decimal places. This summary lets us clearly compare the performance of the 2 execution modes. This script compares how fast a simple TensorFlow neural network runs in eager mode versus compiled mode. It builds a small model with 2 dense layers and runs it on random input data, first using the default eager execution and then using a compiled function. The code measures the average time for each mode over several runs after a few warm-up iterations. It then reports the average execution times and the speedup factor of compiled mode over eager mode. In most cases, the compiled mode runs faster, highlighting the efficiency of graph execution in TensorFlow compared to eager execution. Tracing and graphs. In modern deep learning frameworks such as PyTorch, your model's computations can be represented as a graph built by tracing the sequence of tensor operations during a run. Each operation, like a matrix multiplication or activation, becomes a node, and the data flowing between them forms the edges. This graph does not appear directly in your code, but it is essential for the compiler to analyze and optimize the computations. By using this graph, the system can turn your dynamic Python code into a more static form that runs more efficiently. In PyTorch, tracing records the operations your model performs on real data and turns them into a static computation graph that reflects the observed control flow and tensor shapes. This graph lets the compiler see the structure of your computation so it can optimize it. It can combine small operations, reorder them for better memory use, and remove redundant work. For example, several pointwise transformations can be fused into a single pass, improving performance on both GPUs and CPUs, all without changing your model's logic. When you trace and build graphs in deep learning, remember that the graph represents the exact control flow and tensor shapes from a single run of the model. If your model uses data-dependent branches or loops, that traced graph may only capture one possible behavior. The system can detect when these assumptions no longer hold and retrace the graph, but this adds overhead and can make performance less stable. Models with consistent shapes and predictable control flow benefit most because the compiler can optimize a stable traced graph more effectively. Understanding that the compiler operates on this traced graph helps you anticipate performance behavior and recognize the limits of its optimizations. Python code, tracing and graphs. This script gives a conceptual demonstration of tracing and computation graphs. It manually simulates a very small tensor computation graph so you can see how it works at a basic level. The goal is to help you understand what the nodes and edges represent and how they relate to each other. It also emphasizes the order in which operations are executed within the graph. This part of the code is reserved for any future package installations the script might need. For now, it notes that no extra packages are required, and the example runs using only standard Python libraries. If the script later needs more features, you can modify and enable the provided template line to install the necessary packages. This keeps the script flexible and easy to adapt as its requirements change. We define a node class to represent a single operation in a computation graph. Each node has a name that identifies it, an operation function that specifies what it does, and a list of input node names that provide the values it needs. By linking these nodes through their inputs, we can build complex computations where each node performs a specific operation on the results of previous nodes. TinyTensor is a simple class that stores tensor-like data using basic Python lists. When you create a TinyTensor object, you pass in some values, and the constructor converts them into a list and saves them in an attribute called values. This design lets us perform basic tensor operations in a clear and straightforward way, imitating the behavior of more advanced tensor libraries, but in a much simpler form. The function first checks that the two TinyTensor objects have the same number of elements. It uses an assertion to compare their lengths, and if they differ, the program stops with an error. This safeguard is essential because it ensures that the addition can be done element by element without any size mismatches. Only when the lengths match can the function safely proceed with the element-wise addition. This line creates and returns a new TinyTensor by adding two existing TinyTensors element by element. It goes through both input tensors in parallel, adds each pair of corresponding values, and collects these sums into a list. That list of summed values is then used to initialize the new TinyTensor. As a result, the operation combines the tensors in an element-wise way while preserving their original structure. This function multiplies two TinyTensor objects element by element. It first checks that both tensors have the same length, so they are compatible for this operation, and to avoid size mismatch errors. If the lengths match, it creates and returns a new TinyTensor whose values are the products of the corresponding elements from the two inputs. A list comprehension is used internally to efficiently perform this multiplication across all elements. This line creates a new TinyTensor by multiplying two input tensors element by element. It uses a list comprehension with a zip operation to walk through both tensors at the same time. For each pair of elements, it multiplies them and stores the result in a new list. That list is then passed into the TinyTensor constructor, producing a tensor whose elements are the products of the corresponding elements from the original tensors. We define a tracer class that records operations as nodes in a computation graph. In its constructor, the class creates an empty list called nodes, which will hold each operation node that is recorded. This list preserves the order and details of all operations performed in the graph. Maintaining this sequence is essential for later executing the graph correctly and understanding how data flows through the operations. Inside the tracer class, there is a method that records each operation as a node in the computation graph. It takes a name, an operation, and a list of inputs, then uses them to create a new node representing that specific computation. This node is added to the tracer's internal list of nodes, so the operation is stored and can be executed later as part of the overall graph. The code returns a newly created node object that has been recorded by the tracer as part of the computation graph. This node represents a single operation, including its name, the operation being performed, and its input dependencies. By returning the node, the system allows you to inspect its properties or reuse it in later operations. This makes it easier to analyze, modify, or extend the computation graph as needed. The method starts by creating an empty dictionary to store the outputs of each node. It then goes through the recorded nodes one by one, looking up the required input tensors for each node from this dictionary. Using those inputs, it runs the node's associated operation and saves the resulting output back into the dictionary under that node's name. By repeating this process in order, every node is executed in sequence, and its result is available for any later nodes that depend on it. This function returns an environment dictionary that holds the final results of the tensor computations. In this dictionary, each entry links a node name to its corresponding tiny tensor object. After the computation graph has been executed, you can use this dictionary to look up and access the computed tensor values for any node in the graph. We begin by creating two tiny tensor objects that act as the starting inputs to our computation graph. The first tensor holds three values, 1, 2, and 3, forming a simple three-element tensor. The second tensor also has three elements, each equal to 0.5, so it matches the size of the first. These two tensors are then available for any operations we apply next, allowing us to trace how computations are built from these initial values. We begin by creating a tracer object that records and manages all the operations in our computation graph, allowing us to track their order and dependencies. Then we set up an initial environment, which is a simple mapping from names to tensors. In this environment, the name A is associated with the tiny tensor input A, and the name B is associated with the tiny tensor input B. These named mappings define the starting inputs to the computation graph, and let us refer to the tensors by name as we construct and run the graph. We begin by recording an addition operation in the tracer as a node named C, which represents the result of this computation in the graph. This operation is defined as a small function that takes two inputs and calls the add tensors routine to add them. The inputs to this operation are labeled A and B, referring to the initial tiny tensor objects created earlier. In this way, the addition of these two tensors is captured as a single node in the computation graph. We now add a new node to the tracer that represents a multiplication operation, and we label this node D. The operation is defined as a small function that takes two inputs and multiplies them using the tensor multiplication routine. Its inputs are the result of the previous addition, stored in C, and the tensor B. By doing this, we extend the computation graph with another operation, allowing the tracer to record how values are combined through multiplication. We begin by creating a new environment dictionary from the initial inputs, which sets the starting state of the computation graph. Then we go through each recorded node in order, look up its input tensors in this environment, and run the operation associated with that node. The output of the operation is stored back in the environment under the node's name. By repeating this for every node, we effectively execute the entire computation graph step by step, updating the environment with each new result. We begin by printing a short message to signal that we are about to display the nodes stored in our small computation graph. Then we go through each node in the tracer's list and print its name, along with the inputs it depends on. This gives us a concise overview of the operations that were traced and how they are connected. By examining this output, we can better understand the structure and flow of the computation graph. We now look at the final values of the tensor called C, which holds the result of the earlier addition in the computation graph. Then, we check the final values of the tensor called D, which holds the result of the multiplication. Printing these tensors lets us confirm that both operations ran correctly and gives us a clear view of the final outputs of the computation. This script builds a very simple computation graph in Python, using custom node and tiny tensor classes. It traces operations by recording nodes that represent an addition, followed by a multiplication on two input tensors. When the graph is executed, the tracer processes each node in order, storing intermediate and final results in an environment dictionary. The output shows both the sequence of recorded nodes and the final tensor values, demonstrating a basic forward pass and how later operations depend on earlier ones. Supported operations overview. When you use the compile feature in deep learning frameworks, keep in mind that it works best on certain kinds of operations. Compilers are especially good at detecting and optimizing common tensor operations, such as linear layers and convolutions, by turning them into efficient computation graphs for your hardware. Because these operations dominate models like image classifiers and language models, large portions of such networks can be compiled into faster, optimized code. This is particularly effective on GPUs and specialized accelerators, which run more efficiently with fewer, larger computation kernels. In real-world models, you often use operations that go beyond what the compiler can fully optimize, such as data preprocessing or custom loss functions. The compiler can efficiently handle many standard operations like convolutions and activations, but it falls back to eager execution for parts it cannot optimize. When you introduce things like Python loops or calls to unsupported libraries, the computation graph may split into compiled and non-compiled sections. The model still behaves the same overall, but it now runs as a mix of compiled and eager execution parts. This mixed execution model lets you gradually add compilation to existing projects while still running unsupported parts in their original form, so they do not fail. The actual speedup you see depends on how much of your workload uses operations the compiler can optimize and how well those operations connect. Models built mostly from standard well-supported layers tend to benefit more than those with lots of Python-level branching. To get the best performance, design your critical paths around operations the compiler handles well, while keeping experimental or flexible code in less performance-sensitive parts of the model. Python code. Supported operations overview. This script gives a conceptual overview of which tensor operations are supported, using TensorFlow to demonstrate how they behave. It focuses on how different ways of writing these operations can be more or less friendly to compilation. By comparing compile-friendly and unfriendly patterns, it helps you understand which styles of tensor manipulation work best when you want efficient, optimized execution. The commented line refers to installing the TensorFlow.io GCS file system package, which allows TensorFlow to work directly with data stored in Google Cloud Storage. Because the line is commented out, it indicates that this installation step is optional or may have already been done in the current environment. In practice, You would only need to enable it if your workflow requires accessing data from Google Cloud Storage. We begin the script by importing a few key modules. The operating system module lets us work with files and directories, and the random module provides random number generation for controlled experiments. We then import NumPy for efficient numerical work with arrays and matrices. Finally, we bring in TensorFlow, the deep learning framework we will use to build and train neural networks in this script. We begin by setting a seed value of 7 so that all random operations are reproducible and give the same results each time the code runs. We first set the seed for the standard random module, which controls its random number generation. Then we set the seed for the NumPy random number generator so that any random arrays or values it creates are consistent. Finally, we set the seed for TensorFlow's random operations, which is important for getting repeatable behavior when generating random tensors or initializing model weights in machine learning tasks. We begin by printing the TensorFlow version used in the script. This step matters because different TensorFlow versions can change features and behavior. Knowing the exact version helps you check that the code is compatible with your setup. It also supports reproducibility, since others can run the same version and expect the same results. We begin by creating a small, random tensor to represent model activations with 2 rows and 4 columns. Its values are drawn from a normal distribution and stored using the float32 data type, which is standard for neural network computations. After creating this tensor, we print its shape to verify that its dimensions are correct for the operations we plan to perform next. We build a simple compile-friendly block in TensorFlow using the Keras sequential model with one dense or fully connected layer. This layer has 4 units, so it produces an output vector of length 4. It uses the ReLU activation function, which keeps positive values and sets negative values to 0, adding useful nonlinearity. This design is straightforward and efficient for TensorFlow to compile and execute. We begin by running the friendly block, which is a simple sequential model with a dense layer using a ReLU activation on some random input tensors. Running it once is important because it initializes the model's internal variables so it is ready for later use. After this first pass, we check and print the shape of the output to confirm that the model has transformed the input correctly and that the resulting dimensions match what we expect. This function shows how to simulate operations that are not directly supported in TensorFlow's graph execution. It first converts the input tensor to a NumPy array so standard Python operations can be used, then flattens the array to make it easy to process each element. It squares every value in this flattened list, and then converts the result back into a TensorFlow tensor, keeping the original data type. Overall, it demonstrates how to move data out of the graph, apply custom Python logic, and bring the result back into TensorFlow. The code takes a list of squared values and converts it back into a TensorFlow tensor. It uses the convert-to-tensor function and sets the data type to match the original tensor. This preserves compatibility with TensorFlow operations, so the processed data can be used smoothly in later computations. In short, this step ensures the transformed values remain fully usable within the TensorFlow workflow. We start by sending the activations tensor through a simple neural network layer made of a dense layer with a ReLU activation, which produces an intermediate tensor. We then apply a Python-based heavy transform that converts this tensor to a NumPy array, flattens it, squares each element, and converts it back into a tensor. Finally, we print the shape of the transformed tensor to confirm the dimensions of the output. We first check whether the length of the heavy output matches the total number of elements in the original activations tensor, so we know it can be safely reshaped without losing data integrity. If the sizes match, we reshape the heavy output back into a matrix with the same dimensions as the activations tensor, using the appropriate TensorFlow reshape operation. This preserves the expected structure of the data for later processing. If the sizes do not match, we skip reshaping and instead use the original activations tensor as a fallback to ensure we always have a valid tensor shape for downstream computations. At the end, the program prints the shape of the tensor after it has been reshaped and passed through both the compile-friendly and Python-heavy transformations. This final shape acts as a quick check on the dimensions of the output. By confirming that the shape matches what we expect, we verify that the mixed processing pipeline has preserved the intended structure of the data. This script uses TensorFlow to show the difference between compile-friendly and Python-heavy tensor operations. It begins by setting seeds for reproducibility and creating a small random tensor to represent model activations. A simple sequential model with a dense layer and ReLU activation processes these activations, and the resulting output shape is printed. Then a Python-heavy function converts the tensor to a NumPy array, squares each element using standard Python operations, and converts it back to a tensor. The script reshapes the result back to the original matrix form when possible, and prints the final shape, highlighting how mixing TensorFlow operations with Python-based processing can affect the workflow. Torch compile options. Torch compile basics. You can think of the compile feature as simply wrapping your existing neural network model to make it run faster without changing how you build or train it. You first create and train your model as usual, then pass it through the compile function to get an optimized version. This compiled model behaves like a proxy with the same inputs, outputs, architecture, and loss functions, so your existing scripts continue to work. In practice, you just add this extra wrapping step to speed up computation for models such as convolutional networks or transformers. When you compile a model, it behaves the same as the original, so you can still feed in data, compute losses, and update your optimizer in the usual way. The system first analyzes the operations to build a more efficient computation path, which can make the initial run slower. However, later runs should be faster because they use this optimized path. This allows you to replace the original model with the compiled version for training or inference without changing your existing workflow or the model's behavior. The compile wrapper is built to fit smoothly into your existing software setup, so you can switch between CPU and GPU without extra effort. You can still save and load model weights in the usual way, which makes it easy to try compilation gradually. For example, a team can test a compiled model in a separate branch, while keeping their data processing and evaluation code unchanged. If the compiled model works well, they can adopt it with confidence, since the core programming model stays the same. This makes compilation an optional performance boost rather than a major redesign of the model. Python code, torch compile basics. This script shows how to wrap a model with the torch compile feature while keeping the model and training loop unchanged. It focuses on comparing the speed of the forward pass when using the standard eager execution versus the compiled version. The goal is to demonstrate potential performance gains from compilation without altering the core model or training logic. The commented line is instructing you to install the Torch and Torch Vision libraries, which are needed to use PyTorch. Torch provides the main tools for building and training neural networks, and Torch Vision adds support for computer vision tasks like image processing and using pre-trained models. Installing these packages ensures that all required components are available for the script to run correctly. We begin by importing a few key tools needed to work with neural networks. The time module lets us measure how long operations take, and the random module handles random number generation, which helps with setting seeds and making results reproducible. We then import the main PyTorch library, which we use to build and train neural networks in Python. Finally, we import the neural network submodule that provides ready-made components for defining network layers and complete models. Together, these imports prepare the environment for defining and evaluating our neural network model. To make code produce the same results every time it runs, we use deterministic seeds. We first set the seed in the random library to 0, so its random operations are repeatable. We then set the PyTorch manual seed also to 0, so that PyTorch operations, such as initializing neural network weights, are consistent across runs. Using these seeds ensures that experiments are reproducible and easier to debug or compare. This code chooses whether to run computations on a GPU or a CPU. It uses a PyTorch function to check if a CUDA-capable GPU is available. If a GPU is found, the model runs on it. Otherwise, it falls back to the CPU. This choice is important because using a GPU can greatly speed up deep learning tasks compared to using only the CPU. We define a simple convolutional neural network by creating a class that inherits from PyTorch's main neural network module and initializing its layers in the constructor. After calling the parent constructor, we build a sequence of layers. First, a two-dimensional convolution that takes one input channel and produces 8 output channels with a kernel size of 3 and padding that preserves the input size, followed by a rectified linear unit activation. We then add a second convolution that maps 8 channels to 16 with the same kernel size and padding, again followed by a rectified linear unit. Finally, an adaptive average pooling layer reduces the spatial dimensions to 1 by 1, summarizing the learned feature maps into a compact representation. This line defines a linear layer in the neural network called the classifier, which takes 16 input features and produces 10 output values. It connects the features learned by the convolutional layers to the final prediction. Each of the 10 outputs corresponds to one possible category. This structure is typical in classification tasks, where the model must choose one class out of several options. The forward method describes how data flows through the neural network. It first sends the input through feature extraction layers, such as convolutional layers with activation functions, to produce a feature map. This feature map is then reshaped into a two-dimensional tensor by flattening all dimensions except the batch size. Finally, this flattened representation is passed into the classifier layer to generate the network's output. The code is outputting the result of sending the input through the neural network's classifier layer. This classifier is a linear layer that takes the flattened features from the previous layers and converts them into a final output of size 10. This step is essential because it turns the processed features into class scores. Those scores can then be used to decide which class the input most likely belongs to. We begin by creating an instance of the small convnet class, which represents our simple convolutional neural network model. After creating this model, we move it to the available computing device, either a graphics processor or the central processor. This step ensures that all calculations for the model run on the chosen hardware. As a result, the training and evaluation process is both efficient and compatible with the rest of the script. We use the torch.compile function to create a compiled version of our model, wrapping the original eager model with a compilation layer. This step aims to optimize how the model runs, especially during forward passes, by applying performance improvements that are not available in standard eager execution. The compiled model is designed to be a direct replacement for the original one, producing the same outputs while potentially running faster. We create a small batch of random input data to measure how long our model takes to run. The batch size is set to 32, meaning there are 32 samples in each batch. Each sample has one channel and a height and width of 28 by 28, matching typical grayscale image dimensions such as those in the MNIST dataset. This configuration lets us test the model with input that resembles real image data. We create a tensor of random numbers shaped like a batch of images, with 32 images, one channel, and 28 by 28 pixels. This tensor is then moved to the available device, such as a graphics processor or the main processor. Using this setup, we can simulate input data and test how the model performs without needing real images. To compare the output shapes of the eager model and the compiled model, we temporarily turn off gradient calculations to save memory and computation, since we are not updating any weights. With gradients disabled, we pass the same example inputs through the eager model and record its output. We then pass those inputs through the compiled model and record its output as well. This lets us directly compare the two outputs and confirm that both models produce results with the same shape, without any interference from gradient tracking. The code verifies that the output shapes from the eager model and the compiled model are exactly the same. This check ensures the compiled model can replace the eager model without causing mismatches in output dimensions. By asserting that the shapes are equal, we confirm the two models are compatible in their output structure. This compatibility is important for keeping downstream tasks consistent and reliable. The function first switches the model to evaluation mode so that training-only layers, like dropout, are disabled, keeping the timing consistent. It then turns off gradient calculations, which speeds things up when you only need forward passes and are not updating weights. After that, it runs several warm-up iterations to trigger any necessary compilation steps. This warm-up phase helps ensure the model is fully optimized before the real timing measurements begin. When using a CUDA device, it is important to make sure all previous GPU operations are finished before continuing. To do this, you call the CUDA synchronize function from the torch library, which acts as a barrier for queued GPU tasks. This ensures that every pending operation completes, which is especially important for getting accurate timing measurements and preventing overlap with later computations. To measure how long the model takes to run, we first record the start time using a high-precision performance counter. We then run the model in a loop for a chosen number of iterations, processing the input each time without saving the outputs, since we only care about timing. If the model runs on a CUDA device, we call the function that forces the GPU to finish all pending work, so the timing is accurate. Finally, we record the end time with the performance counter again, which marks the total duration of the measurement. This function calculates the average time per iteration by dividing the total elapsed time by the number of iterations. The result tells you how long each forward pass takes on average. This average time is useful for comparing the performance of different model configurations. We use one warm-up iteration so the compiled model can optimize its execution path before we start timing it. After that, we run 5 measured iterations to evaluate performance. This small number of runs is enough to estimate the average processing time while keeping the demonstration quick and focused. Overall, this setup balances measurement speed with a reasonable sense of accuracy. We measure how long the model takes to run forward passes without including any compilation time. To do this, we call a timing function on the eager or uncompiled version of the model and give it example inputs that represent a batch of data. We set the warmup count to 0 so no extra initial runs are performed. The number of measured runs is controlled by a separate setting, and from these runs, we obtain the average time the eager model needs to process the inputs. We measure the performance of the compiled model by timing how long it takes to process inputs, including any warmup behavior. To do this, we call a timing function with the compiled model and some example inputs, and we specify how many warmup iterations and how many measurement iterations to run. The warmup iterations allow the model and compiler to settle, while the measurement iterations capture steady-state performance. This approach gives us a more accurate picture of the model's true runtime, including the initial overhead from compilation. The script first prints the PyTorch version to confirm that the CRAND installation supports the features being used. It then prints which device is being used for computation, such as a CPU or a GPU. Knowing the device is important for understanding performance and making sure the model runs on the intended hardware. Together, these checks help verify both software compatibility and hardware configuration before running more complex operations. This code measures how long it takes the model to run a forward pass in two modes. First, it reports the average time for the standard eager model, giving a baseline for performance without compilation. Then, it reports the average time for the compiled model, using the same level of precision. Comparing these two timings shows how much execution speed improves when using the torch.compile feature. To check that the compiled model matches the eager model, we compare their outputs by measuring the largest absolute difference between them. We subtract the compiled model's result from the eager model's result, take the absolute value of each element, and then find the maximum of these values. This maximum difference is converted to a standard Python float, so it is easy to read. Printing this value lets us confirm that the two outputs are numerically close, which supports the accuracy of the compiled model. The code compares the performance of the eager and compiled versions of a model by measuring their average forward pass times. It then checks whether the compiled model's average time is lower than the eager model's average time. Based on this comparison, it prints a message indicating if the compiled model is faster. The result is expressed as a clear true or false value in the output. This script shows how to use the PyTorch compile feature to compare the speed of a simple convolutional neural network in eager mode versus compiled mode. It builds a small convolutional model, runs it on either a GPU or CPU, and creates a second copy that is wrapped with the compile function. A random batch of input data is passed through both versions, and the script measures the average time for their forward passes, including a warm-up phase for the compiled model to handle initial compilation overhead. It then reports the average execution time for each version, checks that their outputs are numerically very close, and finally indicates whether the compiled model runs faster, illustrating the potential performance gains of using PyTorch compile. Backends and modes. When working with compilation, it is important to understand backends and modes because they control how your model is optimized. The backend reshapes and optimizes the computation graph to better match the hardware, balancing speed and memory use. Modes determine how aggressively these optimizations are applied and how difficult operations are handled. Together, your choices for backend and mode directly affect how fast your model runs, how stable it is during development, and how hard it is to debug. You can think of backends as specialists designed for different priorities. Some are optimized for general training on GPUs and work well for common tasks like computer vision or language processing. Others push cutting-edge optimizations for specific hardware, offering higher speed, but sometimes with more risk. A research team might choose a more aggressive backend for maximum throughput, while a data science group might prefer a stable one for reliability. Your choice should match what matters most to you, whether that is consistent behavior across many models or peak performance for a particular task. Compiler modes control how code is optimized and how errors are handled. Development mode compiles quickly and gives clear error messages, which is useful when testing new architectures. Performance mode instead focuses on runtime speed, which is better for stable models in production. A common workflow is to begin with a conservative mode to ensure correctness, then switch to a more aggressive mode for deployment, balancing speed and reliability as the project matures. Python code, backends and modes. This script demonstrates and compares simple backend and mode choices using TensorFlow to mimic backend-style behavior. The goal is to highlight configuration concepts rather than focus on specific PyTorch implementation details. Before running it, you need to install the TensorFlow input and output file system package for Google Cloud Storage. Overall, use this script to understand how different backend configurations can be set up and explored in practice. We begin by importing TensorFlow, which we need to build and train our machine learning models. We also import the time module so we can measure how long different operations take. Finally, we import the operating system module, which lets us interact with the system environment, for example, to set variables that help make our experiments reproducible. To make the code behave the same way every time it runs, we set TensorFlow's random number generator to use a fixed seed, in this case the number 7. This ensures that any random operations produce identical results on each execution. We also set a Python environment variable that controls the hash seed to the string 7. Together, these settings make hash-based and random behavior reproducible across runs. This line displays the version of TensorFlow currently in use. Printing the framework version helps you check compatibility, debug issues, and reproduce results. It is especially important because different TensorFlow versions can change features or behavior, so knowing the exact version makes your work more reliable and easier to share. We create a small, synthetic dataset to demonstrate a simple regression problem. Using TensorFlow's random normal function, we first generate input features as 256 samples, each with 16 values drawn from a normal distribution. We then generate the labels in the same way, producing 256 target values, one for each sample. This gives us a basic setup where each input example is paired with a single continuous output value. Before building the models, the code first checks that the dataset has the correct shape. It confirms that the feature data has 16 columns and the label data has 1 column. This validation step is important because it helps catch shape mismatches early. By doing so, it prevents errors that could occur later during model training. This description outlines a simple dense regression model built with TensorFlow's Keras interface. The model is sequential, starting with an input layer that takes 16 features, followed by a dense layer with 32 units using a ReLU activation to add nonlinearity. It ends with a single unit dense layer that produces a continuous output suitable for regression. The model is compiled with stochastic gradient descent as the optimizer, mean squared error as the loss function, and eager execution turned on so operations run immediately, which helps with debugging and understanding how the model behaves. The build model function defines a simple neural network using the Keras sequential API. It takes input data with 16 features, then passes it through a dense layer with 32 units and a ReLU activation to add nonlinearity. After that, it uses a final dense layer with a single unit, which is suitable for predicting one continuous value in a regression task. This structure provides the basic architecture needed before compiling and training the model. We prepare the model for training by calling the compile method, which sets up how learning will work. It chooses stochastic gradient descent with a learning rate of 0.01 as the optimizer, controlling how the model updates its weights. It also uses mean squared error as the loss function to measure how close the predictions are to the actual data. Finally, it enables eager execution, so operations run immediately, making the behavior easier to understand and debug. This function returns the neural network model that was just built and compiled. The model is a sequential network with two fully connected layers, set up for regression tasks. By returning it, the script can later use the same model for training on data or for evaluating its performance. This makes it easy for other parts of the program to access and work with the model as needed. We begin by creating a baseline model that runs in eager execution mode. To do this, we call a function that builds the model architecture using the TensorFlow-Keras sequential interface, which stacks layers in a simple, linear order. In eager mode, operations are executed immediately, which makes debugging and development easier. This baseline setup is important because it lets us later compare how the model performs under different execution modes. We begin by recording the current time so we can measure how long training takes. Then, we train the baseline model using the input features and labels, running for 3 epochs so the model sees the entire dataset 3 times. We use a batch size of 32, meaning the model updates its internal parameters after processing each group of 32 samples. Training is run in silent mode with no progress messages. After training finishes, we record the time again and compute the total training duration to evaluate how time-efficient the eager execution mode is. The code measures how long model training takes when using eager execution by recording the start and end times and subtracting them. This gives the total training duration in that mode. The timing result is then used to compare eager execution with other execution modes. From this comparison, we can evaluate the relative performance and efficiency of different backend styles. We rebuild the model to configure it for graph mode by calling the function that creates our architecture, which uses a sequential model with input and dense layers. This step prepares the model to move from eager execution to graph execution. Once rebuilt, the model can be compiled with graph mode settings. This setup is important because it allows us to compare performance between eager and graph execution modes. The code switches the model from eager execution to graph mode by changing its configuration and recompiling it. In TensorFlow, eager execution runs operations immediately, which is helpful for debugging and development. For better performance in production, it is often preferable to disable eager execution so the model runs in graph mode. In graph mode, TensorFlow builds a static computation graph and then executes it, which can improve speed after an initial warm-up period. The graph model is compiled using stochastic gradient descent with a learning rate of 0.01, and it uses mean squared error as the loss function. Eager execution is disabled by setting the Run Eagerly option to false, so the model runs in graph mode. This lets TensorFlow optimize the computation graph and can improve performance, especially after an initial warm-up period. The code first runs a warm-up training epoch on the graph model to trigger tracing and compilation. This step lets the model analyze its computations and optimize the execution path for later training. It uses the standard training routine with the input features and labels for 1 epoch and a batch size of 32, while suppressing any output. After this warm-up, the model is better prepared to run efficiently in graph mode during the actual training process. To measure how long training takes in graph mode, we first record the start time, then train the graph model on the features and labels for 2 epochs with a batch size of 32. Training output is turned off by setting the verbosity to 0. After training finishes, we record the end time. Comparing the start and end times gives the total training duration in graph mode, not counting the initial warm-up epoch. The code measures how long training takes in graph mode after the model is fully compiled and optimized. It records the start time, then the end time of the graph mode training and subtracts the two. By excluding the warm-up epoch, it focuses only on the main training phase. This timing can then be compared directly to the training time in eager execution mode. This code reports how long training takes in two TensorFlow execution modes. It first prints the time for eager execution, which is simpler and easier to debug, rounding the result to 4 decimal places. It then prints the time for graph execution, which can run faster after an initial warm-up, also rounded to 4 decimal places. Comparing these times highlights the trade-off between development convenience and execution efficiency. TensorFlow offers 2 main execution modes with different trade-offs. Eager mode runs operations immediately, which makes code simpler to write and much easier to debug. Graph mode, by contrast, acts like an optimized backend that can run faster, but only after a warm-up phase where the model is traced and compiled. The time spent in this warm-up is not reflected in the measured graph execution time. Choosing between these modes depends on whether you care more about development simplicity or raw performance, similar to the trade-offs seen in PyTorch's compile options. This script compares eager execution and graph mode in TensorFlow using a simple regression model on a small, synthetic dataset. It first trains the model in eager mode, which is easy to work with and debug, and measures how long training takes. Then it recompiles and runs the same model in graph mode, including a warm-up phase that lets TensorFlow optimize the computation before measuring training time again. The results show that eager mode is simpler but slower, while graph mode, after its initial overhead, runs more efficiently. This illustrates the common trade-off, similar to PyTorch, between ease of development and raw performance. Handling compiler fallbacks. When you compile a model, not every operation will always compile perfectly on the first try. The compiler analyzes and optimizes the forward pass, but if it finds unsupported patterns, it falls back to eager execution to keep the model correct and running. This means some parts, such as custom operations, may run in eager mode while standard layers are optimized. This kind of partial compilation is normal and helps explain performance results without implying there is a bug in your code. When working with model compilation, it is important to recognize fallback warnings, understand what they mean, and decide how to respond. These warnings often indicate that certain parts of your model, such as pre-processing steps that rely on Python lists, are not compiled and instead run in eager mode. To improve performance, refactor these sections to use tensor-based operations or replace unsupported steps with alternatives the compiler can handle. Treat fallbacks as signals that show where your model is being slowed down and use them to guide your optimization efforts. Allowing some fallbacks during compilation can be useful in fast-paced research, where quick experimentation matters more than fully optimized performance. For instance, when trying new attention mechanisms, it may be acceptable for some parts to run in eager mode while others are compiled. In contrast, latency-sensitive systems like real-time speech recognition cannot tolerate even small fallbacks, so those components should be redesigned to avoid them. Overall, you need to balance performance and flexibility by shaping your model structure and operations to fit your goals, while still maintaining correctness and long-term maintainability. Python code, handling compiler fallbacks. This script gives a simple demonstration of how torch.compile handles fallbacks. It uses a tiny model to simulate operations that are not supported. The main goal is to help you recognize the messages that appear and understand how to make small refactors to address them. A line that begins with an exclamation mark is used as a command to install the PyTorch and TorchVision libraries, usually in a Jupyter notebook or similar environment. This ensures the libraries are available for the script that follows. PyTorch is needed for building and training neural networks, and TorchVision adds tools for working with images. In this case, the command is commented out so it serves as an optional reminder for setting up the environment. We begin by importing key parts of the PyTorch library needed to work with neural networks. The main Torch module provides core tools for handling tensors and performing computations. The neural network module supplies components for building network architectures, and the functional module offers useful operations for implementing layers and other network behavior. Together, these imports prepare the environment for creating and manipulating neural network models in the code that follows. We begin by setting a fixed random seed in the Torch library, using 0 as the seed value. This makes all randomly generated tensors in the script reproducible across different runs. By locking in the seed, we get the same sequence of random numbers every time. This consistency is important for debugging and for verifying that results are reliable and repeatable. This code chooses which device to use for computations by checking whether a compatible graphics processing unit is available. It uses the Torch library to see if CUDA support is present. If CUDA is available, it runs on the graphics card. If not, it falls back to the central processor. This lets the program take advantage of faster GPU hardware when possible, while still working on machines that only have a CPU. Fallback.net is a small neural network model built by creating a class that inherits from the main neural network module in PyTorch. In its initialization method, it calls the parent class constructor to properly set up the base functionality. The class also defines a threshold value, which is a floating point number that defaults to 0. This threshold will later be used within the model's logic to control how it responds to input data. In this part of the code, we define a simple linear layer using PyTorch's neural network tools. The layer takes an input of size 4 and produces an output of size 4. It is a fully connected layer, meaning every input node is linked to every output node. This straightforward setup is mainly for demonstration, so we can focus on how data moves through and is processed by this layer. The code saves the threshold value as a property of the model class so it can be reused during computation. Later, in the forward pass of the model, this threshold is used to decide how the data should flow based on the input values. Storing it as an attribute makes the threshold easy to access, compare, and adjust, giving the model flexible control over its internal logic. In the forward method of the model, we first check that the input tensor has the correct shape by confirming that its last dimension is 4. This validation step helps avoid unintended broadcasting problems during later operations. If the input does not meet this shape requirement, the code raises an assertion error with a clear message. This makes it easier to identify and fix issues with the input data during debugging. The model first computes the mean of the input tensor and compares it to a stored threshold, producing a Boolean condition. It then applies a linear layer to the input, followed by a ReLU activation so that all outputs are non-negative. Using PyTorch's conditional selection, it returns either the activated linear output when the condition is true, or half of the original input when the condition is false. This design relies entirely on tensor operations instead of Python control flow, making it more compatible with PyTorch's compilation features. We begin by creating an instance of the fallback class, which serves as our model and is initialized with a threshold value of 0. After creating the model, we move it to the available computing device, either a graphics processor or the central processor. This setup ensures the model is ready to run its computations on the most efficient hardware available. We create a compiled version of the model using the torch.compile function, which takes the regular eager model and prepares it for more efficient execution. This compilation step reduces overhead and can use advanced backend optimizations to speed up performance. It is especially important for testing how the model behaves when compiled, particularly for operations that may not be fully supported by the compiler. We generate a small random tensor with 2 rows and 4 columns using the torch library and place it on the available device, either a GPU or a CPU. This tensor serves as a simple test input for our model. By running the model on this input, we can observe how it processes data and confirm that it is functioning correctly. First, we run the model in its standard eager mode to produce a reference output. We do this with gradient tracking turned off to save computation and memory, since we do not need gradients for this step. The model processes an example input tensor, and we store the result as the eager output. Later, we will compare this reference output with the output from the compiled model to confirm that compilation has not changed the model's behavior. We run the compiled model once with an example input to trigger the compilation process and optimize its operations for later use. This run is done inside a context where gradient calculations are disabled, so no gradients are computed. Disabling gradients is appropriate for inference and helps reduce memory usage while the system prepares the model for efficient execution. To compare the outputs of the eager and compiled models, we measure how different they are. We compute the difference between their outputs, take its absolute value, so it is always positive, and then find the largest value across all elements. This maximum difference is converted to a standard Python float. By checking that this value is very small, we confirm that the compiled model closely matches the accuracy of the eager model. We start by printing the version of the PyTorch framework in use to confirm which release the code is running on. This helps check compatibility and make sure that any features or behaviors we see match that specific version of the library. Recording the version is a good habit with fast-changing libraries because it supports easier debugging and improves reproducibility of results. The code calculates and prints the largest difference between the outputs of the eager model and the compiled model. This comparison is used to check that the compiled model produces results consistent with the eager version. Converting this maximum difference to a standard floating point number makes the result easy to read and interpret. We recompile the model with the full graph option enabled, so the compiler builds a more complete computational graph. This reduces how often the system has to fall back to eager execution, where operations run one by one instead of in the optimized compiled flow. By minimizing these fallbacks, we aim to keep execution more continuous and improve overall performance. We run the compiled full graph model once with an example input to warm up the compilation process. This is done inside a context that turns off gradient tracking, which reduces memory use and speeds up computation because gradients are not needed for this step. We also ignore the model's output, since the only purpose of this run is to trigger and complete the compilation. The code starts by importing the time module so we can measure how long different parts of the program take to run. This timing information is important for performance analysis. By using the time module, we can compare how efficiently different versions of a model execute, such as eager models versus compiled models. This helps us evaluate and improve the overall speed of our code. We define a helper function to measure how long another function takes to run, on average, per per iteration. Pause. To get a more accurate timing, we first run the function a few times without recording the time. This warm-up phase lets any initial setup or overhead complete before measurement begins. Pause. After that, we time a series of iterations and compute the average runtime, giving a clearer picture of the function's true performance. The code first checks whether a CUDA device is available through the Torch library, and if it is, it synchronizes the device. This synchronization step forces any pending GPU operations to finish before moving on. Doing this is important when measuring performance, because it ensures that timing results reflect the actual completion of GPU work, rather than just the start of those operations. We use the time module to record when an operation starts, so we can measure how long it takes to run. By comparing the start time with the end time, we can calculate the exact duration of code execution. This timing information is essential for performance analysis and helps us understand and improve how efficiently our code runs. The code repeatedly runs a function while gradient tracking is turned off. It uses a PyTorch context manager that disables gradient calculations, which is helpful during inference because it reduces memory use and computation. Inside this context, a loop calls the function on the same input a set number of times. This pattern is commonly used to measure performance or observe behavior without the extra cost of computing gradients. To measure runtime accurately, the code first checks whether a CUDA device is available. If it is, it forces all CUDA operations to finish before continuing the timing process. This synchronization step is essential because it ensures that no GPU work is still running in the background, so the recorded time truly reflects the full execution of the operations. This code computes the average time taken for each iteration in milliseconds. It finds the total elapsed time by subtracting the start time from the current time, then converts that duration from seconds to milliseconds by multiplying by 1000. Finally, it divides this millisecond value by the number of iterations and returns the result as a floating point number representing the average time per iteration. This function returns how long an operation took, measured in milliseconds, as a floating point number. Using milliseconds gives a fine-grained measure of time, and the floating point format allows precise values. This precise timing information is useful when you need to analyze performance or compare how long different operations take. We begin by measuring how long the eager model takes to run. To do this, we use a helper function that computes the average runtime over several iterations. The original uncompiled model is tested with a sample input tensor. This gives us a baseline performance measurement before applying any compilation or optimization steps. We now measure how long the compiled model takes to run, noting that it may use fewer fallbacks because it is executed as a fully compiled graph. To do this, we call a helper function that runs the model several times on the example input and computes the average execution time. This average runtime is then saved so we can later compare it directly with the runtime of the same model in eager execution mode. We report a simple timing comparison to show how fast the models run. In particular, we present the average time in milliseconds that the eager model needs for each run. This average is rounded to 4 decimal places to keep the numbers clear while still being precise. These timings help you interpret the performance impact of using the eager model. We report the average runtime in milliseconds for each execution of the compiled model to evaluate its performance. This measurement shows how using the compiled version affects speed. However, it is important to remember that any fallbacks to non-compiled behavior can reduce the expected performance gains. The code compares the average runtime of the compiled model with that of the eager model to see which one is faster. Then it prints a message stating whether the compiled version provides a speedup. This allows you to judge the performance benefits of using the compiled model, while keeping in mind that it may sometimes fall back to slower execution paths. This script shows how to handle compiler fallbacks in PyTorch using a simple neural network with a linear layer and a threshold-based control flow. It compiles the model and compares its behavior and speed to the standard eager execution version. The outputs of both versions are checked to ensure they are numerically similar by measuring the maximum difference between them. The script also times how long each version takes to run, since the compiled model is usually faster, but fallbacks can reduce this benefit. Finally, it reports the PyTorch version, the maximum output difference, and the average execution time for both models to indicate whether compilation actually improves performance. Benchmarking compiled models. Warm-up iterations explained. When you first run a deep learning model with a framework that uses compilation, the initial timing is often dominated by setup work rather than true runtime performance. This warm-up period includes tracing the computation graph, optimizing kernels, and building caches, which makes the first few iterations slower even though the model and hardware have not changed. As a result, if you only measure the first run, you can underestimate the benefits of compilation and get a misleading picture of how the model will perform during repeated use in real applications. Warm-up iterations are like starting a car on a cold morning. Performance is worse at first, while the system gets ready. Compiled models need a few initial runs to do work, such as capturing the computation graph and generating optimized code. After this setup phase, later runs are much faster and more efficient. The same pattern appears in systems like web servers and databases, where early initialization leads to better long-term performance. Because of this, it is important to account for warm-up time when measuring how fast a system really is. When benchmarking compiled models, you should treat warm-up iterations separately so they do not distort your results. If you mix warm-up and steady-state runs, the extra setup work can add noise, especially when comparing to uncompiled models. Instead, run several warm-up iterations without timing them, allowing the system to finish its initialization. After that, start measuring performance so you can clearly see both the one-time compilation cost and the ongoing speed benefits. Python code. Warm-up iterations explained. This script introduces the idea of warm-up iterations by looking at how timing behaves across repeated runs. It uses simple Python functions to mimic how a compiled model needs a few initial runs to get up to speed. The key point is that early iterations often take longer or behave differently, while later iterations settle into a steady, more consistent pattern. By comparing these early and steady phases, the script helps you understand why warm-up is important when measuring performance. We begin by importing 3 standard Python libraries to support our performance analysis. The time library lets us measure how long different operations take, which is essential for evaluating code speed. The random library generates random numbers so we can simulate variability in computational tasks. The statistics library then helps us compute measures like averages, allowing us to summarize and interpret the timing data we collect. We set the random seed to 42, so that any random numbers generated by the script are the same every time we run the code. This makes the results consistent and repeatable. Reproducibility is important when we compare performance metrics or try to debug, because it ensures that we are always working with the same underlying random behavior. We use a small dictionary with a single flag called initialized, which starts as false, to track whether the fake compiled step has been set up. This flag lets us simulate how a compiled model behaves, where the first call can be slower because of initial setup work. By checking and updating this flag, We can control when that one-time initialization happens and mimic the warm-up phase of a compiled model. This function imitates how a compiled model behaves on each step. It first checks whether a compiled cache has been set up, and if not, it briefly pauses to represent the extra time needed for the model's initial run. After this delay, it marks the cache as initialized so that future calls no longer wait. In this way, it captures the common pattern where the first execution of a compiled model is slower due to setup, while later executions run faster. The code first finds the total amount of work by multiplying the batch size by the work scale, which sets how many times the loop will run to simulate the workload. It then creates a running total starting at 0 to accumulate the result of each loop iteration. This running total represents the cumulative work completed as the loop progresses. Inside the loop, we repeat a simple operation for a set number of work units. In each pass, we generate a random number between 0 and 1, then multiply it by a very small constant to represent a tiny amount of work. We add this value to a running total so the work accumulates over all iterations. This process simulates computational effort, similar to how a model might process data in many small steps. The function returns the total sum of the random values it generates during the loop. This total reflects the amount of simulated work done in that step, based on the chosen batch size and work scale. By returning this value, the function provides a simple measure of computational effort for each iteration. This measure can then be used to analyze or compare how much work different iterations perform. The baseline step function represents a simple processing task without any warm-up behavior. It takes a batch size and a work scale, multiplies them to determine how many units of work to perform, and initializes a running total to 0. It then loops through that number of work units, adding a small random value to the total each time to simulate computation. After completing all iterations, it returns the accumulated total as the result of this baseline processing step. Inside the loop, we run a number of small work units equal to the batch size multiplied by the work scale. In each unit, we generate a random number between 0 and 1, scale it by a tiny factor, and add it to a running total. This process simulates a lightweight computational task, similar to a single step in a compiled model. By accumulating this sum over all iterations, we create a measurable workload that lets us time how long these operations take. This function returns the total sum of the random values it generates in a loop. That sum represents the accumulated work done in the simulated step and stands in for the computational effort of a compiled model. By returning this total, the function finishes its role of simulating a workload. The calling code can then use this result for further analysis or comparison. We define a helper function that measures how long it takes to run a given step function multiple times. It takes the step function, the number of iterations, the batch size, and the work scale as inputs. Inside, it creates an empty list to store the timing result for each run. Recording these per iteration times is important for analyzing performance, especially to compare warm-up behavior with steady-state performance. In this loop, we measure how long each simulated processing step takes. At the start of every iteration, we record the current time using a high-precision performance counter. We then call the step function with the given batch size and work scale, ignoring its return value because we only care about timing. After the function finishes, we record the time again and subtract the start time from this value to get the duration of that iteration. Finally, we append this duration to a list that stores the timing for each leap iteration. The function returns a list of times, while each time shows how long one iteration took to run. By collecting these durations, we can study the performance of the function across iterations. This is especially useful for compiled models, where early iterations may be slower because of initialization overhead. Comparing early and later timings helps us understand the model's warm-up behavior. We configure our simulation with a batch size of 32, which sets how many units of work are processed at once, and a work scale of 120, which controls how much work is done per batch. We also define 2 warm-up iterations to represent the initially slower performance of a compiled model. After this warm-up phase, we run 5 measured iterations to observe the steady-state performance. Together, these settings keep the simulation fast and safe, while clearly showing the effect of warm-up on performance. We begin by running a baseline timing function to measure how long a sequence of operations takes without any warm-up behavior. To do this, we call the timing routine with the baseline step function and set the total number of iterations to include both warm-up and measured runs. We also provide batch size and work scale values to define how much work each iteration performs. This configuration lets us collect timing data that represents stable performance without being distorted by initial setup delays. Before running the compiled timing tests, we reset the compiled cache by marking it as uninitialized. This forces the fake compiled step function to behave as if it is running for the first time, with a slower warm-up performance. Doing this reset is essential for correctly simulating the warm-up phase of a compiled model, and for accurately comparing warm-up performance to steady-state performance in later runs. We run a function that simulates one step of a compiled model across both warm-up and steady-state iterations. It takes parameters for the total number of iterations, which combines warm-up and measured runs, as well as the batch size and work scale. For each iteration, we record how long it takes to execute. By comparing the timing of the early warm-up iterations to the later steady-state ones, we can see how performance changes from a cold start to a stable execution phase and better understand the behavior of the compiled model. We split the list of compiled execution times into 2 parts to study performance. The first part, called the compiled warm-up segment, contains the initial iterations that are slower because the system is still warming up. The second part, called the compiled steady segment, includes all remaining iterations that reflect stable, steady-state performance. By separating these 2 segments, we can clearly compare the early warm-up behavior with the later, more consistent behavior. We first compute the average time of the baseline iterations to get a typical duration without any warm-up effects. Then we calculate the average time across all compiled iterations, which includes both the warm-up and steady-state phases, to see the overall compiled performance. Finally, we compute the average time using only the steady-state compiled iterations, excluding the initial warm-up, to better understand performance once the system has stabilized. The code begins by printing a short header that explains the purpose of the experiment. It tells the listener that the script will compare how a baseline model behaves versus a simulated compiled model that uses warm-up iterations. This introduction sets the context, so the results are understood as a performance comparison between these 2 approaches. In other words, it prepares the reader to focus on differences in behavior and speed between the baseline and the compiled version. We first print the times for the first 3 iterations in the baseline scenario to see the initial performance without any warm-up effects. Then we print the first 3 iteration times for the compiled scenario, where the early iterations are slower because the system is still warming up. Comparing these 2 sets of early iteration times lets us clearly see how warm-up affects performance, and how the compiled steps differ from the baseline at the start. We first report the average time for all iterations of the baseline step to establish how long the non-compiled version takes on average. Then we report the average time for all iterations of the compiled step, including the initial warm-up, to see overall performance with the slower startup phase. Finally, we report the average time using only the steady-state iterations of the compiled step, excluding warm-up, to show how fast the system runs once it has stabilized and better reflects repeated real-world use. The code explains that compiled models run more slowly during their initial iterations because they are in a warm-up phase. These early runs are not included when measuring performance, since they do not represent typical behavior. Instead, the code focuses on the average time of later iterations after warm-up, because this steady-state timing better reflects how the model will perform in repeated deployments. This script illustrates how warm-up iterations affect performance measurements. It compares a simulated compiled function, which runs slowly on the first call and then speeds up, with a baseline function that runs at a constant speed. By timing several iterations of both functions, it shows that the compiled version appears slower at first because of the warm-up phase, but becomes faster in steady state. The script then computes average times over all iterations and over only the steady-state iterations, demonstrating that excluding warm-up gives a more accurate view of real performance in repeated deployments. This highlights why warm-up effects must be considered when evaluating and comparing execution times. Reliable timing techniques. Once your compiled model is stable, you should carefully compare its performance to the uncompiled version. Keep hardware, batch size, input shapes, and pre-processing the same so that any differences you see come from compilation itself. When you time the models, exclude unrelated overhead such as data loading or network transfers. Focus only on the forward and backward passes to reveal the true impact of compilation on computation speed. To get reliable timing results, run your model multiple times and summarize the measurements instead of trusting a single run, which can be distorted by background activity or scheduling delays. Discard the first few warm-up runs, then compute statistics such as the average time and how much the results vary. By looking at a collection of measurements, you can detect and ignore outliers. This approach is especially important on shared or busy machines like cloud instances or personal laptops, where other tasks may interfere with performance. When timing GPU operations, you must account for asynchronous execution to get accurate results. Many GPU tasks return control to the program before they actually finish, so you need to insert a synchronization point before stopping the timer to ensure all work is complete. You should also keep the environment stable by avoiding other GPU workloads and minimizing power changes. By controlling these conditions and handling asynchrony correctly, you can obtain reliable timing for comparing model performance. Python code, reliable timing techniques. This script shows how to measure execution time in a reliable way. It uses TensorFlow to simulate running a model, while focusing on three key ideas. First, it performs a warm-up phase so initial overhead does not distort the timing. Then, it repeats the execution multiple times to get more stable measurements. Finally, it uses synchronization to ensure all operations finish before recording the time, leading to accurate and consistent performance results. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. Using this exact version helps ensure the script runs correctly and that results are compatible and reproducible. The exclamation mark shows that this is a shell command intended to be executed from within a Jupyter notebook or a similar environment that allows running system commands directly. We begin by importing several Python modules along with TensorFlow to prepare the environment for our script. The operating system module is available for system interactions, even though it is not directly used here. The time module will later let us measure how long parts of the code take to run, and the random module provides random numbers to introduce variability. We also import NumPy for efficient numerical work with arrays. Finally, we bring in TensorFlow, which is the main library we will use to build and run machine learning models. We begin by setting a seed value of 42 so that any random operations in our code are reproducible. This means that each time we run the program, the random results will be the same. To achieve this, we set the seed for the random module, for the NumPy random number generator, and for TensorFlow's random operations. Using the same seed across these libraries helps ensure consistent behavior in experiments and model training. The script first prints the TensorFlow version to confirm which setup is being used and to check compatibility. It then tests whether a GPU is available by listing the physical devices and turning that result into a simple true or false value. Knowing if a GPU is present is important because it can greatly improve performance compared to running the same computations on a CPU. We build a small neural network with the Keras sequential API in TensorFlow to benchmark execution time. The model takes input data with 128 features, then passes it through two dense layers with 64 units each that use the ReLU activation to add nonlinearity. It ends with an output layer of 10 units using the softmax activation, which is suitable for multi-class classification. This simple architecture provides a straightforward setup for measuring how long model execution takes. To build and verify the model, we first create a dummy input using TensorFlow's random uniform function, generating a tensor shaped 32 by 128 to simulate a batch of data. We then pass this dummy input through the model to perform a forward pass and obtain an output. Finally, we check that the output has shape 32 by 10, confirming that the model's architecture and output size are correct and that it is properly initialized for later use. We define a compiled forward function using TensorFlow's function decorator with just-in-time compilation turned on. This tells TensorFlow to optimize the forward pass of the model for faster execution, similar in spirit to using compile in PyTorch. Inside this function, the input is passed through the MODI, which runs it through all its layers and returns the result. Using this compiled version lets us benchmark how the model performs when compiled and compare it directly to its performance in regular eager execution. The function starts by defining a helper that measures the average time needed to perform a step in a process. It accepts another function to run, the inputs for that function, and settings for how many warm-up and repeated runs to perform, along with a label to identify the measurement. It then creates an empty list to store the timing results after the warm-up runs are finished. This structure enables accurate measurement of execution time, which is important for benchmarking and comparing performance. The loop runs through both warm-up and measured iterations, timing how long a model step takes. At the start of each iteration, it records the current high-resolution time, then calls the step function with the given inputs. If a GPU is used, it forces all GPU operations to finish so the timing is accurate. After the step completes, it records the end time. For iterations after the warm-up phase, it computes the elapsed time and stores these durations in a list for later analysis. The code converts the list of recorded times into a high-precision numeric array, then computes the mean and standard deviation of these times. Both results are converted to standard Python floating point numbers for consistency. It then prints the label along with the mean time and standard deviation rounded to 3 decimal places, and reported in milliseconds. This produces a concise numerical summary of the timing results for that label. We begin by creating a batch of random input data using TensorFlow's random uniform function with a fixed shape of 32 by 128. This gives us inputs of consistent size for every run, which is important for fair performance comparisons. We then check that the generated data actually has 32 rows and 128 columns. Verifying these dimensions helps ensure the input matches what the model expects and prevents unexpected errors during execution. Before measuring execution time, the code first warms up both the eager and compiled execution paths. It runs the model once with the prepared inputs to get the eager path ready. Then runs the compiled forward function with the same inputs to prepare the compiled path. This warmup allows any initial setup or caching to complete. As a result, the timing that is recorded afterward reflects steady, ongoing performance rather than one-time startup overhead. We measure how long the model takes to run in eager mode by using a timing function that repeatedly calls the model on a fixed random input batch. To stabilize performance, we first run 3 warm-up iterations that are not included in the final measurement. After that, we record the execution time over 10 runs and compute the average. We label this result as the eager forward time so it can be clearly identified in the output. The code measures how long the compiled forward function takes to run by calling a timing helper with that function, the input data, and settings for warm-up and repeated runs. A few warm-up runs let the system stabilize before actual measurement, and multiple repeats improve the accuracy of the timing. The results are labeled as compiled forward time so they can be clearly identified. This timing process is used to compare the performance of the compiled execution path with other approaches. This script shows how to measure reliable execution times in TensorFlow by simulating model runs. It first fixes random seeds for reproducibility and checks for a graphics processor, then builds a small neural network and runs a dummy pass to initialize it. The code defines an optimized, compiled version of the model using just-in-time compilation and compares it with standard eager execution. After a warm-up phase, it repeatedly times both versions and reports the mean and standard deviation of their execution times. The results highlight how compiled execution can differ in performance from eager execution and help quantify the efficiency gains of using compilation in TensorFlow models. Interpreting speedup results. After you measure timing for both the eager and compiled versions of your model, you should interpret the results in terms of speedup. This means comparing how long each iteration takes to see how many times faster the compiled model is than the original. For example, if eager mode takes 20 milliseconds and the compiled version takes 10, the compiled model is twice as fast. Keep in mind that this speedup is specific to your particular model, input shapes, and hardware, and changing any of these can significantly change performance or even remove the benefits of compilation. When judging speedup, do not rely on a single timing number. Look at the distribution and stability of the results to see if the improvement is truly reliable. If the compiled model is faster on average, but its timings vary a lot, you may need more runs or a more controlled environment, since shared hardware like GPU servers can add noise. If the compiled model is consistently faster than the eager version and shows similar or lower variability, you can have more confidence in the speedup. It also helps to compare the average time with a high percentile measure, so you understand both typical performance and behavior under tougher, production-like conditions. When judging speedup from compilation, you need to weigh the runtime gains against the cost of compiling. For large models, the initial compile time can be high, so consider how many iterations you will run and whether that upfront cost is justified over the full job. In long training runs, a few minutes of compilation may be negligible if it improves throughput by 10 or 20%, but for short inference jobs, the overhead can outweigh the benefit. You should also think about how compilation affects startup latency and whether it can handle dynamic inputs in your real application, and then decide if compilation is worthwhile or if an eager execution setup is better. In this lecture, you learned to describe the purpose and high-level behavior of torch.compile in PyTorch 2.10.0. Wrap existing nn.Module models with torch.compile and configure basic compilation options. And measure and interpret performance changes after compilation, including warmup effects. In the next lecture, Lecture B, we will go over profiling and tuning. Thank you for your attention. See you all in the next lecture.